All right, here we go. Example 5 on 8.2, we're finding polar area. And remember, just for kicks and giggles, humor me. The area is what for polar area? The integral from a to b, or alpha to beta, r squared dx d theta. All right, Tex, you couldn't uncover. Yeah, there you go. All right, and it's frozen. Yeah, there you go. All right, so there it is. So we're using that every time. So we know how to find areas of parts of one graph, but remember in 6.2 we learned how to find area between curves. We can do the same thing with polar curves. So these are the more interesting ones. Find the area inside this function, but outside that function. All right? So step 1 is going to be the same as it typically is. Draw the graph and identify the region. If you have the wrong region, you're probably going to get the wrong answer. So I'll do the first one with purple. Okay, purple. Here we go. 3 sine of theta. This is where knowing what they look like helps. What does 3 sine of theta look like? It's a circle with what type of symmetry, X or Y? Y-axis symmetry. The diameter is 3, and it traces out once from 0 to pi. Yeah, and because it's a positive 3, it's going to trace out like this. Now, this is where you want to kind of draw your pictures a little bigger than maybe normal, okay, so that this up here is 3. If that were negative 3 sine, of course, it would live below the x-axis. Now, you can always just pick quadrantial angles, 0, pi halves, pi, 3 pi halves, 2 pi. Put your dots and try to connect the dots and see what it looks like. So we got to be inside that one. Let's go ahead and shade it. There we go. Shaded. And now the next one I'll do green. So it needs to be outside the next one. Well, the next one, 2 minus sine of theta. Y'all remember what that one is? Well, it belongs to the family. This is the dimpled one. Okay. Let's go ahead and graph that one by looking at quadrantial angles, because maybe we're not sure. Sine of 0 is 0, so we start by coming out here 2 units. So this is where it starts. At pi halves is 1, so 2 minus 1 is 1. So it comes up to here. It's 1. Pi, sine of pi is back to 0, so we're out here at negative 2. Sine of 3 pi halves is negative 1, so we end up with 2 plus 1, which is 3. That's negative 3. And then we hit 2 pi and we get it again. So this is the one that it looks something like this. It never reaches the pole. 2 plus 1 is 3, that's the maximum radius, and 2 minus 1 is 1, that's the minimum radius. So it needs to be outside that one. So you can kind of see the region, right? Yeah, let me go ahead and shade, I'll shade that one as brown. We're looking for this region right here. All right, so the part that's not purple. So here's where we have to have a plan of attack. And this is where drawing your radial lines is kind of important. Did I get that right? Inside, okay, I identified it wrong, yeah. I should have done where they intersect. Inside the purple one and outside. So let me just, let's just do that one. There we go. So now we want the region up there that's not shaded twice. Yes? Yeah, see, so I identified the wrong region. I read carelessly and forgot what it was. Okay, so now that we've got it identified, let's draw our polar lines. What's interesting about polar curves is just because you see the 2 lines crossing each other, that doesn't mean they intersect. Wow, why? What does that mean? Well, think about it. If you went out into the snow and you saw tracks of footprints that crossed each other, that doesn't mean that the people or the animals that made those tracks bumped into each other, does it? Okay, so just because the curves cross each other doesn't mean they intersect. In rectangular mode, they do intersect when they cross. They could have gotten there at different times. So we want to make sure that if they do intersect or they cross paths, we want to make sure they happen at the same angle. So if you draw your first radial line from here to here, from the center to that point right there, that could be our starting value for integration, yes? And if I start integrating then from there, wherever it is, I'll call it alpha for now. And then I start integrating from there up to, bless you, this was pi halves. I can integrate up to pi halves. We'll call that beta. Could I use symmetry here? Yes, both of my curves have y-axis symmetry, so I think I'll use symmetry because it's kind of nice. So that would give me all of the purple region, but now that's too much, isn't it? So now I need to come back and subtract out the part that I don't want, which would be starting at the same angle, subtracting out this beefy brown part. See that? And that gives me what's left. So it's not always top minus bottom, but in this case it's big minus small. So let's go ahead and set it up. The area of the region is twice, and I'll go ahead and put a big bracket because I'm using symmetry here. I need to figure out what theta is. I need to figure out where they intersect. So let's come off to the side and do that. Intersect. We'll have 3 sine of theta. That's one of them. And it equals 2 minus sine of theta. That's the other one. So we'll do this as much as we can without a calculator. So if I bring the sine across, I end up with 4 sine of theta equals 2. So sine of theta equals 2/4, which is a half. What is the first angle then where sine equals a half? Pi 6. Okay, so I know that this angle is in fact pi 6, and I know that they both actually cross there at the same time because of where they start at 0. All right, so now I've got my interval of integration. So I'm going to have a 1/2 the integral from pi 6 to pi halves. Now, because both the green part that I traced out and the brown part that I traced out are both from pi 6 to pi halves, I can set it up as a single integral. Okay, so here's what I'll do. I'll do r squared, let me put another bracket there, minus r squared. Kind of like the, what was it, the washer method, d theta. Let me move this out of the way. Oops. If they were over different intervals, and we'll see one like that here in a second, we'd have to set it up as 2 separate integrals, which you're allowed to do that here as well. You could do 1/2 one of them, d theta, minus 1/2 the integral of the other. All right, so the one that goes first is the one that creates the most area, which is the purple one. So that's the 3 sine of theta. And don't forget to square it. And then we'll subtract on the same interval using the green curve. See that? And the green curve was the dimpled limicon. So that's going to be 2 minus sine of theta. And then it's squared. Yeah. So this, in fact, is the setup. And from here, again, if you had to do it by hand without a calculator, we haven't used the calculator yet, you would have to use the power reducing identities for sine, and then you'd have to square, multiply, double square the second one and use the power reducing again. So it's a lot of labor to do it by hand. But symmetry would at least help in getting rid of the awkward 1/2 in front because you're doubling it. Let's go ahead and go to the calculator now that we have it set up. And unless you need the calculator to find points of intersection, I would say don't even use it. Okay, so I'm just going to go straight to the home screen. I am in polar mode. No big deal. I'm in polar mode. So 2 times 1/2 is 1. So I'm not going to bother with that. I'll just go straight to Math 9 from pi 6 to pi halves. And now we talked yesterday, the parentheses that the calculator provides are like the big brackets that I put. So we need another set here. Parentheses 3 sine of theta, which is going to show up as theta because I'm in polar mode. Close it for the angle, close it for the function, and squared it. So if you have the parentheses in the wrong place there, you might not square the 3. Or feel free to just call that 9. Minus another set of parentheses, 2 minus sine of theta. Close it for the angle, close it for the quantity, and square it. And then click to the outside d theta. So now you hit enter. You trust that you typed it in carefully. Maybe double check, triple check. 5.196. Okay? I've already done that. When you set up your integral, thank you, Nolan. When you set up your integral, you want to make sure that your integral is set up for the whole thing. All right? So that when you do come back, you don't forget to double it. All right? So I wrote it like that, which is why I could ignore the 1/2 when I typed it into the calculator. Okay? But that would make a great other answer choice on a multiple choice, right? That number doubled, or maybe that number halved, or both, right? Okay, so there you go. There is your first example of the area betwixt 2 polar curves. Wasn't that bad? But notice if you draw it kind of small, you're not seeing it as well. So make sure you draw these exceptionally large. All right. Today's National Something on a Steak Day. Does anyone know about a something on a steak joke that's clean? What do you call a boomerang that doesn't come back? I don't know. An alligator with a sword through it? A steak. Uh-uh. That's my favorite joke of all time. Yeah. That encompasses my entire personality right there. What's brown and sticky? A steak. Yeah. All right. So if you want, we could kind of put our polar curves on a steak, right? A blue steak. So there you go. That would make a wonderful lollipop. Maybe some cotton candy or something. So on a steak. All right. And 5.196 is our answer on a steak. All right. That's how we can celebrate. All right. Example 6. Do we have time? Do we have time? We're in here until 45. Okay. We have 20 minutes. Let's go. Find the area of the common interior. Common interior. Common interior. That means it's inside or all three of them, right? Oh, both of them. They only gave us both. All right, so r equals 3 cosine theta, and r equals 1 plus cosine theta, and look at that. Look at that. Do y'all notice something different about the word and? Yeah, it's Comic Sans right there. Boo. Boo. All right, little subtle. That's like an Easter egg, a calculus Easter egg. All right, let's go ahead. Let's go ahead and identify the two curves. So I'll do 3 cosine of theta in pink. That is going to be a circle. Good. So if you plug in a 0 for theta, you're going to start at 3. I'm going to go out even further. There we go. And it's going to trace out like this once from 0 to what? Pi. And then 1 plus 1 cosine theta is going to be a it's a cardioid, right? Because the coefficient and the constant are the same. It's a cardioid. And it traces out once from 0 to 2 pi. So let's go ahead and trace it out with the quadrantal angles. When I plug in a 0 for theta, cosine of 0 is 1, 1 plus 1 is 2. So I'm going to start right here. At pi halves, I get 1. At pi, I get 0. At 3 pi halves, I get 1, so I'm down at negative 1. And then I come full circle to 2. So it looks something like this, and it bounces off, and it does that. All right. Now this is kind of important right here. This is what I'm talking about. You see those two lines, the pink and the green, they cross on my graph? Do they actually intersect there though? They actually don't. Okay? Because I know on the green graph, I hit that point at an angle that's greater than 3 pi halves because I just passed the negative y-axis. But for the pink function, I know that I've already made it all the way back around by the time I've gotten to pi. So those are the two paths that crossed in the snow, but the people who made them did not bump into each other. So I'm going to try and use symmetry here. This is the other place where the curves cross. Do they actually intersect there? Yes, the way they trace out, they actually do. Okay? So I'm going to try and use symmetry. The common interior would be, oops, that's too much. The common interior would be inside both the pink and the green. So is this right here? The common interior? All right, so now I need to come out with a plan of attack. Draw your radial lines. It's so important to draw your radial lines. So I'm going to go ahead and use symmetry. It has x-axis symmetry. So if I start at 0, I can start looking at my little slices, polar radial lines, all the way up using the green curve up to there. I can use the green curve up to there, so up to this angle. But then I have to integrate from that to pi halves, and there's a little sliver in there. Y'all see it? That I haven't got yet. Now I got to switch curves and go from that angle. I got to get the rest of this little sliver, which I'll do in red, up into pi halves. Okay, so I know that pi halves, no, that's pi, sorry, that's pi. Well, let's see. I have to use both curves here, and I'm not getting too much. I'm actually doing part of it and then adding it to the other part. So let's go ahead and see where they intersect first. Intersect. I don't want to get ahead of myself. Intersection. You got 3 cosine of theta equaling 1 plus cosine of theta. So if you collect like terms, you're going to end up with 2 cosine of theta equals 1. So cosine of theta is a half. And of course, what's the first positive angle where that happens? That's at pi thirds. So notice they do not intersect down there at 4 pi thirds. Okay, mathematically it didn't come out that way. They only intersect at pi thirds. So I know that angle. So let's go ahead and do this. The area, we'll set it up as we go. I'm going to double it again. I'm using symmetry. Yeah. I'm not there yet. I'll wait on that. Okay? So I'm going to go, it is pi halves. I'm going to go 2 times 1/2 the integral, and I'll use green because I'm starting on the green curve. So it's going to be integral from 0 to pi thirds of r squared. And that's going to be on the green curve, which was the cardioid, so it's 1 plus cosine of theta squared. D theta. And now I have to switch. I have to switch to get the rest of it, so I need a new integral. Plus 1/2 the integral from pi thirds to, yes. Now because I'm on the pink curve, when I start at pi thirds, I'm going to get to this spot right here at the origin at pi halves. Okay, which is because, again, the entire pink circle traces out in pi. That would be halfway through its rotation. So that's at pi halves. Oops, my third looks like a half. Let me rewrite it. Pi thirds to pi halves. And then that's going to be on the other one squared, which is 3 cosine of theta. So this is where it kind of gets confusing if you look here, because if you get caught up looking at the green curve in this region, the green curve doesn't hit that polar 0 until pi. But that pink curve, remember, it never journeyed into quadrant 3 at all. It went straight down, right there. So we got there at pi halves. All right, so with all of that, those 2 separate integrals, each with their own d theta, and the 2 out front, is that the setup that works? If you look at that. Have I already doubled it, Colin? Yes, okay. And remember, if you left this d theta off right there, you're going to lose points, because now you're essentially saying the next part is also part of the integrand. So let's go to the calculator now. And I think if I distribute the 2 to both integrals, neither one of them would have the 1/2. Are you all okay with that? All right. So again, if this is a calculator question, maybe you've already put them in y1 and y2. Let's go ahead and practice that. We're using the calculator now, so you might have them in there. So R1, I'm going to put as 3 cosine of theta. It's the first one that they listed on the question, so I'll put it in there as R1. And then I'll put 1 plus cosine of theta in R2. Now, here's what you could do on your paper to help you. You could actually call this R1. I would call it R1, not a subscript, and call this one R2. You can rename them R1 and R2, all right? And down here then on your setup, you can actually use that. You could say R2 squared and R1 squared. Because it's an intermediate and not your final answer, you could do that. All right, so now let's go to the home screen. And we'll type it in. So again, the 1/2 divides out with the 2. So we get the integral from 0 to pi thirds. And instead of typing in 1 plus cosine quantity squared, again, that one is in R2. So alpha trace number 2 squared d theta. And again, you could also do this in function mode, but you would have to then type in the actual equations because you couldn't refer to r. Plus, again, the 1/2 is gone, so just another math 9 from pi thirds to pi halves. Thank you. I did it again. Pi halves of the other one, which is what I have in R1. I also did 2 times pi. Thank you. So alpha trace now number 1. Don't forget to square it. D theta. So a quick double check of that to make sure everything looks good. Make sure you got your R2 and R1 correctly in there, because if you did the wrong equations here, it's going to be wrong. And enter. And you get your answer, 3.926 or 927. Be careful if you truncate in another class. College Board allows you to truncate, and therefore I allow you to truncate. Other teachers may not want you to truncate. Right, Gorel? Okay. All right. So there you go. So there is one where they intersect, but you're not subtracting on the same interval. You actually have two separate pieces that you have to combine on different intervals to get you the whole thing. And again, that little sliver is really, really hard to see. So if you make your graphs large enough, and then you draw your radial lines. As you draw your radial lines, you're mentally accounting for everything. Okay, so you can shade it as you go, essentially, to know that you got it all. All right, how much time do we have now? 12 minutes. All right. Any comments or questions on number 6? Or any other something on a stick jokes? The answer on a stick. Okay. That comedian does the on a stick, right? The Jose Jalapeno on a stick. Jeff Dunham, that's the guy. That's the guy. All right. Let's try it. Do we have time for example 7? We have like 10 minutes, and this is like a free response. I don't think we have time for example 7. So here's what I'm going to do. I'm going to stop right there for today and give you, I'm going to give you the rest of the class to start the worksheet. In 10 minutes, you could probably get one of them done, all right? And then tomorrow, I know Ban's going to be gone tomorrow. I'm going to record the lesson in class tomorrow, and you can watch it at your leisure over your 3-day Easter weekend break. So that when we get here on Monday, we'll finish up the polar area easily on Monday, if not tomorrow, if we go fast enough. So on Monday, we're either going to be finishing this stuff up and then rolling into Chapter 9, or starting with Chapter 9 directly, okay? All right.